So this is my review on my first paper, which is a hybrid approach combining control theory and artificial intelligence for engineering self-adaptive systems. This was written earlier in 2020. So the problem the paper tries to address is in self-adaptive systems, in order to adapt, there needs to be a strategy, or there can be multiple strategies. They can also be formed at runtime, and this can be quite computationally expensive. And the authors attempt to show how artificial intelligence can be used in conjunction with control theoretic principles in order to make this process more efficient. Why is this still a problem? Well, while control theoretical techniques have been shown to provide formal guarantees about the effectiveness and robustness of self-adaptive systems, it can be quite computationally expensive when it comes to dynamic adaptation, and the authors state that there is a lack of literature on the use of artificial intelligence in self-adaptive systems. So the related work for this paper mainly revolves around fairly generic principles regarding control theory and how that's used in self-adaptive systems, that it can provide formal guarantees on the performance of a system and how stable it will be, and things like whether it will converge and essentially achieve what the goals that have been set for the system. So the main idea of this paper is to integrate artificial intelligence with control theory. So this diagram kind of shows the whole system. This is the managed system, and the idea is to have, well, this is the manager that essentially controls the system. The idea is that we have the strategy manager that formulates a strategy for all adaptations to be guided by, and that can essentially, there are a number of different strategies that the system could put in place, and the strategy manager, the authors use the word or the term that it synthesizes adaptation strategies, which suggests to kind of form a strategy based on components of all the rest. So to form an optimal strategy. And this strategy gets sent to the strategy enactor component, and that is essentially what enforces the strategy to take place on the system, or the strategy that the system is to be guided by. And there's a feedback control loop that is kind of that links the target system with the enactor, but it goes through the enactor optimization component. And so these optimization components are there to essentially reduce the time that the time that the strategy manager and strategy enactor components will take at performing their jobs. So basically, the manager optimization component will try to essentially use machine learning techniques such as regression and evolutionary algorithms. In this paper, they specifically use the NGSA2 algorithm, which is a genetic algorithm, to find an optimal solution space for the strategy manager to search within. And it also has a granularity Here on this diagram they've put gain, but in the paper it's kind of described as granularity, which is essentially how small should the steps be in the search space. So whether it should be kind of high exploitation or low exploitation of a given area of the search space. So this component is essentially to find the optimal values using machine learning so that the strategy manager will be as efficient as possible and also do a very good job because it's been given a good solution space according to all of the knowledge within the system. The enactor optimization component essentially tries to optimize the values of the PI controller, so the proportional value and the integral value, and it then sends these to the strategy enactor, which then uses a PI controller in order to, I guess, maintain or make changes to the system if necessary. And I believe that's, so there's another diagram here which kind of shows how it works. So a strategy is sent from the strategy manager to the enactor, which is this whole component, that is sent to, or combined with, so this essentially gets knowledge from the system, or from the end of the feedback loop of how it's doing. That gets combined with the goal that is intended for the system, produces an error, and if there needs to be an adaptation, then it goes and the enactor performs an action and then adapts the target system. Now, if the authors say that if the system is not reacting in the way that is intended, then the strategy enactor can send an exception to the strategy manager, which essentially says it needs a new strategy formed or given to it in order to guide the system by. That then gets sent back to the strategy enactor and it can continue its work. So how is this better? Basically, these extra components are there to reduce the time of strategy formation and optimization, and hopefully as well increase the quality of an adaptation. So to evaluate this solution, they use the body sensor network, which is basically it's where the health of patients is monitored with sensors, and these sensors send their data to a centralized processor which analyzes that data, and the sample rate of the sensors needs to be adapted so that it doesn't overload the centralized processor. So that is essentially the control of the system, is to control the sample rate of each of the sensors. These were the fairly general questions that were asked by the researchers, and that is basically the thing, the whole paper. In general, they had good results. They said that it managed to produce good performance overall, and compared to not using these components. My critiques are these, are stated here. Basically, the English wasn't overly good, so it was hard to understand parts of the paper and how everything fit together. It would have been nice to have a specific example of what an adaptation strategy looked like for someone who's not for people who are not familiar with adaptation strategies. And there seemed to be an appearance of conflict between components. So if I go back to this diagram, this uses, essentially this is controlling with a PI controller the system and adapts the system in this loop. And I don't really understand how a strategy would need to be changed, or how an exception would need to be sent from an enactor to the manager to get a new strategy so that the system would behave as intended. It kind of seemed like they both had the same job to do. So that was my, I guess, biggest critique, was how all of this fits together. So that is the end of my presentation.